Hello, everybody. My name is Ellie. I'm Nicole, and our advisor is Dr. Kim, and we are the Autonomous Navigation Robot Guide Dog Group. So today we're just going to go over a project overview. We're going to go into our components, the diagram, the way everything is flowing. Some of our major things are our April tags, our stereo camera, motor control, communication, and then we'll just have a summary with our budget and everything, just going into some further details. So, all right, so as you could probably imagine, we're kind of geared towards visually impaired individuals. So our audience is visually impaired individuals. Sort of like for our project, we were kind of thinking more so children. We kind of imagined like a school where this kind of technology could be used to help children who are visually impaired. And our main reason is that service animals can be very expensive, and then due to training time, and everything, it's really hard to get a service dog. I don't know if anyone ever had that experience. I have like a family member who was trying to get a service dog, and they've been on a wait list for years. And not only that, it's also an animal, right? So there's obviously a lot of care that goes into service animals. So our solution is to sort of have a robot replacement, right? So we want to be able to safely escort these individuals to their identified classrooms. Armstrong Hall, if you guys don't know, is like one of our engineering complexes at TCNJ. So that's the example we're going to be using for this project. And we just want to create efficient algorithms that are going to be able to be implemented into the TurtleBot3 WafflePi, which Nicole is going to go over in a minute. It's the robot that we're using. And again, the specifications, Armstrong Hall. And what we want the robot to be able to do is identify room numbers. So like, for example, like, let's say I want to go to blank classroom, the robot should be able to know where it's going, right? So it should be able to navigate if there's any obstacles in the way, if there's people in the way, it should be able to manage that. The starting point, it would just be the side entrance to Armstrong. So you can sort of think of like you're coming into the building and the system is started. And then the endpoint would be, for our example, the robotics lab. And we're using software, so we're using the April tags and computer vision, which is a main component, and then the hardware, which we'll be going into.
So for the components, we are using the TurtleBot WafflePi. It's the device you see at the top. A major reason why we selected this robot was because we already had it in our lab, as well as it was applicable to our project, and it uses open source hardware and software, which was very helpful for us. And then for microprocessor, we ended up choosing the NVIDIA Jetson Nano. After a lot of testing with the Raspberry Pis, we found that we had a lot of compatibility issues, specifically when working with a stereo camera that we purchased. So we switched to the NVIDIA Jetson. And then for our main controller board, we are using the OpenCR board, which is basically Arduino. It came with the TurtleBot WafflePi, and the purpose of this is to control our motors. And then lastly, for our cameras, we selected the ArduCam stereo camera. It's a little pricey, but because of the purposes of our project, we wanted to spend more money on the actual vision aspect because it's more of a vision project. And basically what this camera does, it's a dual camera method that is able to replicate human vision and view depth and create disparity maps. And as I said, it allows for object detection, so being able to identify objects in the user's way, or identify like the QR codes that I will talk about later for identifying the room numbers.
Okay, so then moving on to our block diagrams to just have like a better idea of how everything is flowing. We're first just going to start off with our system architecture. So we have like the PC and the terminal, and that's going directly in communication with our TurtleBot. And then with our TurtleBot, we have our main autonomous navigation system, which works directly with our motors, our stereo cameras, and our distance sensors. And then we also have a communication module, right? As you can imagine, we need to have some form of communication between the robot and the user. So like communicating, there's an obstacle in the way, we're going to go left, something like that. And then we have this sort of dog control, which is a push button, and you can sort of think of that as like the leash components. Like, let's say I like my shoelace was untied or something, and I needed to have an emergency stop. That would kind of be what that control is for. And then for our block diagram, it's just sort of like how the system will be working. So we have like the main on and go button. So if the robot is on and the system is going and we're moving, we have our communication system, which is the sort of voice recognition. So we're sort of working on this still, but like kind of like if I were to say stop, it could stop. Right now, we're still doing like the hard push button sort of thing, but that's what that would be for. And then the stereo cameras, which is like the main component of our project, right? If we see anything, that's going to be directly related to the motor controls, which is the servo and the steppers. And then also sensors, which are just for added security on the side, just to make sure like if the hallway is open, the sensors will be able to detect that for turning and stuff like that. And then if the robot is off, then it's just off. So that's that. And then we just have a video sort of demonstration as a visual.
And everything seen in this video, we will be explaining more in depth later. So you just have like a real idea of what we are talking about later on. So here you're just getting input from the user. It checks a file and then it's going to the said location. Right now we are controlling it using a keyboard node. And then detecting obstacles with the stereo camera. And then those were the April tags we just saw. So distance confirmation, so the room numbers.
And again, we will go.
And then, so going into April tags, as you just saw, basically they are QR codes. So behind each QR code lies text. So we were able to link each QR code because they each have an ID number to a room number in Armstrong Hall, the engineering building. So they are a judicial system used in robotics and for camera calibrations. And they allow for longer detection ranges and accuracy. And a major reason why we chose to use this is because I don't know if you are familiar with text, but it's very difficult to identify text given like specific lightings in specific rooms or different things like that, or like different angles you're at. But with April tags, depending on the angles, it doesn't really matter because it's able to identify QR codes from like longer distances and ranges. And here are just some tests that we have. So in the images at the top, you could see each QR code, April tag. If it's the correct QR code, it says yes on the top left. And if it says yes, and it's at an X distance amount away from the specific door, at the top left, it says stop. But if it's not, it says no. So like that we were working with, so being able to do that and then incorporate something similar later with the actual system stop and go was our goal.
Right.
And then here's just a snippet of our code. So what it does is it loops over the April tag detection. You could see at the bottom here, the current destination, that's what was printing out as you saw in the last slide before. So it prints out the current destination and the user's inputted destination. And then here's a quick video of how that works. So it compares the tag of the April tag to the specific room number. It gets user input. And depending on if it's X distance away that we set it, it will be able to tell the user to stop or move depending on how far it is.
So as like Nicole said, we're trying different angles and stuff. This is the correct room. And then once it's a certain distance away, it should say stop. So that would be like the motor control trigger. So it's able to identify the correct room and then it's also able to stop from a certain distance. So then moving on to our stereo camera component, I don't know how familiar you guys all are, but stereo cameras are basically just two cameras that are close together. You can think of it as how we see with two eyes. And the reason that we're using them, the TurtleBot actually comes with a LiDAR sensor. We've specifically chosen not to use the sensor. If you can think about them, they're actually really expensive. So just like in a more future aspect of this were ever to be like produced, it'd be a lot cheaper. And there's actually a lot of research going on with like self-driving cars. We're trying to replicate stereo cameras to replace a lot of sensors. And with stereo cameras, we're able to create things like depth maps. So we're able to have better distance control and estimation. And as you can see, it's just an example of what the two cameras look like just for your retrospect. And then we also have what you just saw, which is like just a CSV file with like the tag numbers, and then we correspond them to rooms. So what you can kind of imagine is that outside of each door on the bottom, because that's where the robot would be, there would be like the tag, and as it's walking down the hall or just going down the hall, be able to read those tags. And then if it's the correct tag, then you're able to have that kind of stop and go system that you just saw.
And then going to motor control, currently we have two different ways of controlling the robot, but as of now, they have to be altered because we just wanted to have a good sense of how to actually control the motors before actually implementing them, because the user itself, because they are visually impaired, they shouldn't have ability to actually move the robot, and it should do that automatically. So the first way is using a keyboard node. So you could just see the motors running here. And basically by running ROS, we are able to have access to a keyboard node. The user is able to use the WASD keys in order to move the robot. And then here's a different way. It uses a controller. And similarly, the user won't have access to use the controller because they are visually impaired. But what we found was that the top right button of the controller allows the user to stop. And this is something that we may implement because it's easier for instead of implementing like a separate push button that the user would have access to, because this remote controller was already working with the TurtleBot and it came with it. It's an easy fix to being able to have the user stop and go whenever it's done. And then for communication, we are using Pi serial. So as you can imagine, we need to have the NVIDIA Jetson communicating with the OpenCR motor controllers. And how we are doing that is using Pi serial. At the top right, you could just see a snippet of our code, of our testing code. So currently, this is the Arduino, and it's asking for user input from the Jetson. And at the bottom, you can see it says enter your room destination. That's done through the Jetson. And then it takes the user input and then it outputs it to the Arduino. And then based on if the motor is correctly run, it says that you have arrived to your correct destination if they match.
So just a summary of everything. I know we just kind of threw a lot at you, but basically like our completed tasks, we have sort of every kind of like individually modularized working. So really our main thing is just kind of getting everything together. But as you just saw with Nicole, the able tag detection, so that's like a main component, just being able to have these codes working and identifying them to rooms so that the robot is able to know where it's going and where in retrospect as well. The camera setup, which is the stereo cameras, the serial communication, which Nicole's went over. Right now we have like an LED system. So we kind of have like a place for that code to go. We have like the logic working. So right now we have it where you can input a room, and then once it sees the room, the LED actually turns on. And what we want that to be replaced by is the motors, right? So, and then like if it's too close, the LED, like a red light will go off. So that would be the motor stopping. So that's what we currently have. And then, yeah, the motors just need to be independently working. We're still trying to figure out like what works best logistically. As Nicole was saying, like we don't want the user to have like a huge reliance on themselves to control the robot, right? It should be really independent and working for the user. So we're trying to figure that out. And that's basically what our current tasks are, just trying to get that incorporated and doing a lot of testing. Moving on to our hours chart, as you can see, the red line is our predicted and then the yellow is our actual. So we're going above. And then for our budget, we did go a little bit over budget. The main reason for that is our batteries. So the TurtleBot actually comes with a LiPo battery, but as we figured out earlier this semester, or actually last semester, is that it was not working. So we had to buy a new battery basically. But besides that, we didn't go too over. I think, yeah, that's basically it. Are there any questions?
Speed of the rover just explained. Walk as many years more slow.
It's really
It's
slow.
very slow. If you
Like,
saw in the
it's
video,
safe.
like if you try to do it walking speed, like the motors will like overheat and then it would stop.
Yeah.
Like it's very slow.
Yeah.
So what about like I understand we're limiting it to a single building. Do you understand like a map of that building, like where the rooms are in relation to each other?
So with the TurtleBot, there is like the LiDAR component that we like specifically did not want to use, but that isn't a capability. So like you're able to do mapping and you would be able to like do a map of like whatever building you want to and like pick a point and it should be able to go there. So that is a capability.
Yeah, so if you were to exit this room and go to 105, you would understand that it needs to go to the elevator.
Yeah.
At the end of the wall,
Yes.
then down, and then which direction to go. You go, okay.
Yes.
If you were to implement SLAM, that's what the LiDAR uses. But because of our purposes, and we're like basically creating LiDAR from
Through the
scratch,
stereo camera.
like we would never get to that point with the time frame that we had.
Okay.
Yeah, but that is definitely a possibility. Yeah.
Just distance.
like camera distance and proper stopping. I was thinking identifying the tags and the camera had to get really close to the tags before the vehicle will tell itself to stop. And I was thinking, well, potentially some issues if the April tag is like really high off the ground, and then the whole line, of course, is basically driving forward. So depending on how high up the April tag is, it might not stop in time to keep running to the wall. That's just one thing.
So two things. The tag is going to be like on the ground for the robot specifically. So like that's kind of why we almost had like a school setting. Like this would be, if you could like think of this being a product, it would be like installed as a system in a school. So it'd be like something that like the kids use, right? And also that distance we just had because we actually wanted it to be super close, so that's harder to test, right? If it's able to detect it from like back here and it's stopping, we don't really know how sensitive it is. That's just like a line of code we changed. So definitely like as an actual use, we would
be able to like alter and test what the best distance is before the robot like turns into the desired class.
Right.
How is your user going to like be guided? Is there a string? Is there a physical leash? Like, is the controller tethered to it?
Right now we don't have anything created, but what we were thinking is using like something like a suitcase handle type thing, so the user would be able to hold that and the suitcase handle would be connected to the actual robot and you wouldn't be able to like move it. Do you know what I mean? Like instead like the robot would be guiding you with that.
like if you can think of like an actual seeing eye dog, they sort of have like those handles on the harness. And actually like as we were kind of advised by Dr. Katz, like he's basically like whatever an actual dog like service dog does, just try and do that. So we're kind of like trying to go along with that.
Is the path the robot takes in the hallway, is that generated on the fly by the camera, or did you have to like train the robot like, where hallways are in the midst of it, or does it always go down the middle?
Right now we have it so that the robot would always be on the right hand side because like people walk on the right hand side. And we have it so that there's an X amount of distance from the wall that the robot's in. But if there was an obstacle per se, like we have the robot so that it would go left around it and then go back to the right side, same distance from the wall. Any other questions?
That's purely using stair cam to train the distance before.
We also like are going to implement the ping sensors that are both on the sides. There's two. And that's like majorly for the distance from the wall. And also like if you're going down the hall, there's an opening, it'd be able to detect that for turning and stuff like that.
How many of them in the
Well,
There's two right there. I think we have like 7, 8,
out of how many?
14.
we have a lot in computer engineering. We only have one in electrical.
Yeah.